Recording has started.
Okay, so today we will go to the convolutional neural networks. This is again a review session in the sense that hopefully this is not the first time you have seen CNN, so that it goes a little bit quick again, right? So just you refresh, but just in case if you really never seen CNN before, or at least not familiar, then you have to spend more time. I think this one covers pretty much. Let's say if even you haven't seen CNN before, read carefully, read the code provided carefully, you should be able to do the homework as well. So yeah, but hopefully you have seen that. So we will go relatively fast. Let's talk about what we will cover today. Okay, so we will talk a little bit about motivation. And this one we will go roughly quickly. I mean, compared to FCN, right, or multi-layer perceptual, the fully connected neural networks. So why we want a CN for image. And then we will talk a little bit about modules and so on. So typically design what you have. And then we will talk a bit about general regularization techniques like dropouts and batch normalization. Those are you frequently see in a lot of neural network designs. This can be regarded as that. Then in the last, we'll quickly mention the ResNet. We will have a homework exercise to do that. And throughout the lectures, we will have some PyTorch examples, just so that you can work with that. Okay, so yeah, so basically this is what we are planning. Okay, so let's move. Okay, so for CN, of course, we start with image classification. So that's the common task, and it's really start to popularize the images, right? So for RGB image, which is a color image, you have so-called three channels, and you have an image size. I mean, we will use the PyTorch notation. PyTorch notation, basically, the first will be channel, the RGB. Second will be heights, and the third will be width. And then this one, you have 1,000 classes, right? So this is what you are looking at. This is training data, so which we use notation before, and where X is the image, Y is basically one of the labels for image. Like, for example, it's whether it's a cat and so on. So this is actual image. This image is not from the ImageNet. It's just some image. But basically, you want to classify this, right? So basically, yeah, this is the problem. Then the question, of course, is so why we want to do CNN and what it is, right? CNN called convolutional neural nets, right? To understand what CNN, right? So why we want to use CNN, we first want to say what's wrong with fully connected in neural net, and what's the main difference, right? CNN and fully connected is certainly you can apply fully connected to this problem, especially when image is small. So but for the image net, like 200 pixels, right, or even larger, then you times 200, 200 times 200, you have a high dimension. It's like 500,000 dimension. So it's I mean, actually, yeah, it's something like it's pretty large. So then the problem becomes you really cannot too many parameters. Basically, you cannot do that parameter well. So CNN does that by so-called you have used a much fewer number of parameters, right? So that's a key. And you have a parameter sharing, so-called. You can think about you can think of the specialized FCM, but with fewer parameters. Then use convolution. Convolution, it will capture the basically invariance of transition of the image. Basically, you just move the image from one small patch to another small patch, horizontally and vertically, with a small patch, and you hope all the operations on this small patch are the same. So that's the idea. If we can look more later. Essentially, you can apply these kind of things, right? If you think about the small patches images, you're first starting to do the within this patch, basically local features like edges, textures, and so on. They can be directly captured by using the convolutional operator. It's like a small FCN within a small region. So you can think about that. But then you have to do that sequence in a sequence so that you can form a more global view of the image. So that's another idea which we will come to. And once you combine these two, then essentially you are okay. Then in the end, you make it a smaller feature map. It's like embedding of your image. And then you can pass to another FCN, the fully connected neural nets. Yeah, so basically, CNN is starting to extract features. They are aggregating local features together into higher level features. By doing that, each time they look at a small neighborhood, but then you can ask, if you do small neighborhood, how you do the global one, right? So that's what we'll explain later on. Essentially, by using the smaller neighborhood, using smaller number of parameters, then you could aggregate that together. You get some you basically get what you want in the end. So yeah, so key is one is you have a smaller number of features each time, and you have a hierarchical manner so that you can aggregate local to global, and then you basically you're basically doing that. So we will talk about the details soon, but this one is the idea. So one thing about that is once you go through CM, right? So how do you capture the global one? So the way it does that is try to, downsample the image. So the higher resolution, you get the local features. And once you go to the more later layers, right, the resolution reduce. Resolution reduce if you see, and then they capture the more global little bit. Once you capture the later reduce to be even smaller in the end, right? You will capture basically even more global information. So this is actually where how it manages by capture each time using a smaller local combination, but you form global feature by combining local features together. So this is a hierarchical, and this is how it works. Okay. So basically, yeah, there is one of downsampling, which is important in the CNN design, and all the CNN does that for this purpose. The purpose really is try to capture more global information rather than local information. Okay. Yeah, so why useful, right? So I mentioned you use a smaller number of parameters instead of a fully connected. It's just too large. The parameter is just too many. You cannot really effectively learn. And it's smaller, much learn. And also it's aligned with the image structure. There are some there is invariance across when you do the shifting, when you do this both through the horizontal and through the vertical, right? So this reduced number of parameters, and you always have a local perception field. Always manage the local, right? That's another thing, right? Yeah, this is translation environment means this is good for the image structure. And the hierarchical learning is early detects like features, deeper using the more complex, but this one is by using downsampling. Local feature with a downsampled image, and you actually will be able to get a global. Now there's one thing. I think it's actually in the previous one we mentioned that the channels, right, starting to increase when you downsample. The reason of that again is we will come back to that. It's actually is basically mitigate the loss of information. When you downsample the image, you lose some information. You up the channel means each pixel, instead of 3 colors, you have many more features represent each feature. So it will capture the global information around that. Around that. So here it is, and we will go one by one soon about these convolutional neural network modules. You start with regular grid data because they require these translation environments, right? So they do the translation. Regular grid data. CNN are designed for image with a kind of neighboring structure. You can also generalize to some other structures like a graph CNN and so on, but we will not talk about those. We focus on for the images in this example. Convolution, you just aggregate the local information. So that's all it does. You have a filter, aggregate the local information. Usually it's a 3 by 3, the modern design. I mean, used to be they have a 5 by 5, 7 by 7, but now mostly they only look at the 3 by 3, but a few times, right? If you have a 3 by 3 twice, it gets like a 5 by 5, but it's more effective. You also have a nonlinear activation function. This one is the same as FCN. So you basically apply this nonlinear to get the nonlinearity. If you remove all the nonlinearity, then you have a linear model, right? It's like just FCN. If you remove nonlinear, you get a linear model. So this one is just adding the only nonlinearity coming from here, more or less. Oh, there's another nonlinearity is pooling. Pooling reduces spatial dimension. As we mentioned, right? When you go through CNN, you first get, because your filter always local, right? You get local information. You can get a lot of layers of local to make it global, but more effectively you reduce the dimension. You reduce this feature dimension, and then you immediate local becomes more global. So this is a hierarchical setting about your CNN. Yes, you are actually doing that, and yeah, and then you have a fully connected layer. Yeah, typically, before the fully connected layer, you could also do a pooling. So we'll comment on that. Just making it in the final layer before that. But essentially, this is more or less what it is. Okay. So here is a PyTorch code. You just say 1 CNN. Yeah, so basically, this one is just getting one single convolution, right? They have different parameters, which we'll talk. In sample, this is the first layer. In sample is like SGD, RGB. RGB will 3, right? 3 in sample. It say out channels is 16, right? 16 means each pixel is instead of represent 3 numbers by 16 numbers. It's a vector of dimension 16 for each pixel. Kernel size is 3. This one is basically what we will talk later. Mostly we will just use 3 by 3 kernels. So at least in the most of the modern CNNs. Stride is something we will briefly explain, and the padding is kind of important. We will come back to that. And the stride dilation, there's other things which appear, but used less often. Stride is more important, I would say, than dilation, a little bit more frequent. So we will explain that. And then this one, you just say 1 CNN layer, right? So you first go to a convolution, then go to a ReLU. It's just like going fully connect the linear layer, ReLU, right? Which is for the typical one, but this one is just for this, okay? Usually when you create, recall that when we create input for PyTorch, right? The first one is actually not the data itself, right? It's a batch always. You have a batch size. It's the number of data in your batch. This one we discussed in the in whatever the SGD, right? When we go through the code, and the other one then essentially is by touch convention is you have a first dimension of your data is a channel, right? And the second will be height. The third will be the width, right? So this one is the tensor. So let's look at the representation about image in terms of so-called feature maps or channels and so on. Three-dimensional tensor will be an image. We ignore this batch dimension. It's always there. You just keep in your mind. You always add another dimension always in front. It's a batch size, right? Basically means many more data. Here we just say one data, one of the images. So for one of the images, you have a channel, height, and the width, right? So this is the height, width. Channel is actually the depth. Here is like a RGB, right? So this is like 3 channels, but you can map it much more. So for each pixel, then you have channel is a number of real numbers to represent a pixel. Basically, you can think of that a feature map, the dimension of your feature to represent each pixel. For RGB, it's a 3. For others, it's actually can be more. Usually, you increase immediately once you start from the RGB. Let's say for grayscale image, right? What is the channel? Right, it's 1, right? So if you grayscale, you have 1, right? The channel is just one number. RGB is the 3. Yeah. And in our case, if we work with MNIST is a grayscale image, so we just have 1 channel instead of 3 channel as input. If you work with the ImageNet, it's a 3 channel, it's a color image, okay? So in features, they're all created by feature map. And the nice thing about the channel, the concept is you have a more complex representation of each pixel. That representation can encode actually the surrounding information of the pixel, not only just the RGB, right? But something about a more global view of the pixel. So each time you are forming these features, and that features will be useful. And each time you can have a different number of features. So for each of that. Basically, you are thinking what you are learning is in this feature map. Basically, this is like a feature representation of your pixels, right? Each pixel have representation. They will encode things like, is there an edge? Is there some textures? And so on. Or even say there might be an object. This might be nose of this cat, and so on, right? So it encode a lot of information. How do you get that, right? How do you do this CNN? So starting with the CNN, we starting with channel, so-called in channel, right? And this is usually we have odd. I mean, it doesn't have to be, but in our case, we just write because that's more conventional. Usually, in our case, the K. This is a so-called kernel, right? So basically. This is usually 3 by 3, right? So basically K is 1, then 2 times 1 plus 1 is 3. The 3 by 3 kernel with the K equals 1, so we just write that. It could be, it doesn't have to be 3 by, it could be 2 by 2, but this is more conventional. Extract local features. So it slides over the input feature map, compute the weights across a small dimension. Oh, yeah, this one is a space about spatial dimensions, right? So basically, this is a convolution. In mathematics, this is called convolution. This is the kernel. Essentially, you're just looking at, essentially, if you look at each pixel, right? Each pixel, right, you just apply this, the smaller window. If you have 3 by 3 kernel, it's a 3 by 3 window around that pixel with that centered, the pixel in the center. And then you just say, I will make this 3 by 3, just making it more like a fully linear feature. So it's you have a channel is a C, right? 3 by 3 is 9. So 9 times C is your input linear. And then you apply, this is like linear operator. It's you apply this dimension, and then you get. You could also add bias, by the way, so as always. But essentially, this is the output of your small linear operator. In the case of a 3 by 3 kernel, and C is a dimension, you have a 9 times C number of number, right? So then you just apply. This is for each output, right? Each of these you generate output. And this one, guys, become another image, right? Because this operation is for all the pixels. So it will be another image. And it spans all channels for the inputs. And so the number of weights, if you calculate, right? So if you have 3 by 3, it's a kernel is basically 9 times C, right? So for each of that, without the bias, right? And the convolutional layer, it doesn't produce one output, right? It starts with a C in, right? It generates C out. So you have many of these kind of features, right? So this small kernels is 9 C parameters for each output. Then you have C out, 9 C in parameters. So basically you have a 9 C in times C out, number of parameters total. It's a matrix becomes. And then this kernel will produce C out real filters to produce this output, right? So this is basically how the convolution operation works. Mathematically, it does that, but essentially it maps the image with the C in inputs and using a small linear operator around the kernel to be an output. And the size of your parameter is 9 times C in, C out instead of your image size if you do not use a convolution. So convolution is in 2D CNN. Basically, each has a size of this, right? So this is a filter, and the total is in channel, out channel, and possibly the bias is a number of parameters. This is where the parameter share comes in, where for each pixel, they share the same number of parameters. You apply the same operation for every pixel, right? So basically, this saves your model size. Channel refers to the depth of input and output, right? You have out channel, you have in channel, right? So basically, this is how it works. By the default, if you think about what is image size, right? You can think a little bit. Imagine you have 3 by 3 image. Image itself just 3 by 3. We just say it's 4. Then you have a 3 by 3 kernel, right? How many you can actually, if without padding, right? What is the size of the image, right? If you think about 3 by 3 image, right? Kernel is 3 by 3. How do you do convolution? At the boundary, it's not well defined, right? So the only thing you can do is the center. So essentially, if you have a 3 by 3 image with 3 by 3 kernel, you left out without padding, you have a 1 by 1, just for the center. Okay, so that's how. So basically, padding is just say, oh, we want to. I mean, you could do that. This actually people sometimes without padding. Then that's you just reduce. If you have 3 by 3, reduce by 2, right? Reduce by a size of 2 for each dimension. Because you cannot do that on the boundary, but the padding is you try to make it a little bit larger so that the output will be the same as your original image. So here is right. Here is basically a calculation. Again, just thinking about 3 by 3, right? And the k is 1, and then you have basically left up a bit 1 by 1. Okay. Because at the boundary, there's no way to do convolution to define that anymore, unless you do padding. So padding is one parameter with frequently used. You have to pay attention to that because otherwise you change your image size, right? If you don't want to do change your image size, you have to give a proper padding, right? So for the, if you look at that, basic padding is apply usually 0. You can do other things, but typically just 0 padding along the boundary. It's like give a border of a certain black color, right? You can think about which dictates your boundary, right? And then you know it's just a 0. Cannot be applied at the borders, reducing the spatial dimension. This one is typically what you see when you have when you actually have without padding, right? Now, how many padding you need, right? So think about that. What is a padding? Padding usually, applied for each side, right? So for a kernel of size k, 2k plus 1, not k, we know the reduced dimension about 2k, right? And therefore, if you apply padding, its padding should be size of a k in order to, because it's apart each side. So, and for example, if you look at the 3 by 3, you have a padding size of 1, it becomes 5 by 5, because each one you're adding 1, right? And with 5 by 5, you can have when you ignore the boundary, everything is okay. So you have you produce a 3 by 3 when you have a convolution. So yeah, so within. So because at the boundary, you cannot do convolution. You have to shrink by 5 into 3 by 3. So basically, this padding allows you to maintain the image size. Padding equals k, you just apply, p apply to all sides. Then you can say, okay, what is p? 2k, then you enlarge image. But usually people don't do that because what you enlarge is pretty much 0 somewhere. But p equals k is pretty frequent. Just make sure your output image is the same as your input image, right? So for 3 by 3, usually your padding size is 1. That's frequent. You could do padding size 0 or 1, right? Yeah, padding typically adding the zeros right around of your inputs allow kernel to be centered at every pixel of original image. So that's basically what actually padding is. We will quickly mention the stride and the dilation, right? So we don't want to say too much about that. This one we use less. Stride is probably more useful in some sense. Sometimes people do use a stride. Dilation sometimes used, but less frequently. Stride also will be needed when we talk about transpose convolution or deconvolution. Later on, we do the generation. They need a stride. But stride, roughly speaking, so let's look at essentially the formula is here. And then you can read the math formula, but loosely what it does is the following, right? S is the stride, then which determines how far the kernel moves at each step. Basically, what happens is when you have size, let's say, is 6 by 6 image, right? Stride of 2 roughly get the 3 by 3. There are some boundary effect, padding and so on, but ignore that. It just divide by 2. Stride makes your shrink, yeah, basically this is what it. Dilation mostly is simulated like a 5 by 5 kernel with a 3 by 3 or something like that. You are enlarging your kernel, but filling a lot of places with 0. So it's yeah. Question? Yeah.
Isn't dilation like similar to doing transposed convolution?
Dilation is not. Dilation here actually is dilate your kernel, not your spatial. Stride is actually in the transpose. It's actually still is a stride. Yeah, dilation is thought about it's a dilate image, but it's a dilate kernel. Yeah, it's a right. Stride is more about the spatial dimension. Dilation is about the kernel dimension. Yeah. Okay. Yeah. But anyway, so yeah, we will comment on the I think the transpose later on. Yeah. But strike reduce the dimension in the standard kernel, right? The standard convolution. And yeah, dilation, you just you just make a kernel appearing larger, but insert a lot of zeros. So that's what it is. Yeah. We are yeah. Let's try to say Yeah, this is about that. We will not give too detailed. I mean, you could do the calculation yourself, how many padding and so on you need and so on for the stride in particular, right? So, and then you can play with that. But essentially, I mean, it's similar. You look at that operation where it's well defined, and then you have a calculation about how many you need, right? To get a chip. So activation layer. So after that, we do activation, which apply the basically, it applies activation is really just how do I say? Just it's a nonlinearity. It's only nonlinearity. And for a lot of neural net design, I would want to just comment on even later transformer and so on. All the nonlinearity somehow it's simple. It's always element-wise. They just keep that nice, okay? And so linear has to do a lot of things because nonlinear just element-wise. So all the interactions, everything you think this one interacts with that, mostly done by linear. That's always the case. Yeah. There's a ReLU, and then that's all. So yeah. So basically, convolution is a linear, right? Itself is a linear. It's just a smaller parameter shared fully connected neural net. You can think about that. And this one now becomes linear, and then that's all. Okay, so let's talk a little bit about the downsampling. Downsampling is important, as we mentioned. We want to have a image, right? Image with a high, let's say 200 pixels. You eventually reduce that because once you reduce that, a small kernel becomes more global, correspond to more global information in the original image. So downsampling, facting, make it hierarchical, make it global. And you usually apply this called max pooling. You could also do average pooling. You can always do stride the convolution. Max pooling is the simplest, and it introduces additional nonlinearity in some way. Basically, it's put a max of that. Basically, this is pooling. Then you get that. This one you can achieve downsampling we mentioned by strided convolution, but most people you could do that. Most people do that with max pooling, just separate. Also, it's introduced slightly additional nonlinearity that actually turns out to be helpful, which is interesting. Yeah. So here is max pooling. So this is the more complex nonlinear. Basically, you pick the max of let's say 2 by 2 of your max pooling, right? Max pooling with size 2, then essentially you just look at the 2 by 2 kernels, you get the max. So they are non-overlapping kernels, you just get the max. So that's all it does. So you pull the information by using additional max. I think people do that basically just it's helpful. You could also do average, right? Average here, just average this guy, yeah. But this one is helpful. So now what is the purpose of this pooling, right? So the purpose of pooling is the following. So first it's a downsampled image, reduce the dimension. Reduce the dimension so that you are doing more global, starting from local, going more global. It also increases robustness. At the global level, shifting doesn't matter as much. Somewhat it absorbed into the feature map, so it helps. And it lowers computation also because image becomes smaller now, right? You have a smaller model, and so a lot of things, if you think about that, for the CN, once you goes to higher layers, and it becomes smaller. So a lot of computation actually happens in the bottom layers because they are larger images, and you are doing the convolution. And the smaller image, when you do convolution, it's a smaller cost. Max pooling, this is where, right? So this is some max. We see the example, and you can do the average as well. So if you want, You can also have a stride in the pooling, but you can also have a stride in the convolution, achieving similar. If you have a stride convolution, it's more similar to average, right, than the max. Now the question is, right? So you usually at this stage, right, when you do the pooling, you usually want to, actually the pooling itself doesn't change the channels, right? If average pooling and max pooling, another thing is that there's no trainable parameter. It's like a ReLU. It's just the operation. This is a linear. This is nonlinear. So people prefer the nonlinear here. And there's no change of channels. It just apply. It just only changes the spatial dimension. However, so usually when you're starting to do this before the pooling, right? When you do the convolution, you want to increase your channel, right? Essentially, when you downsample, roughly thinking, at the pooling, you are going to downsample your image, right? So when you downsample the image, you are losing some information, spatial information at least. Now you want to compensate by increasing your feature representation complexity for each pixel to compensate, to regain certain information. It doesn't have to be all the information, but certainly this is a kind of a design which is pretty typical. You are increasing your channels and reduce the spatial dimension simultaneously. So here is a map which you actually try to get. CM, right? So basically, you have input, you have a convolution layer, you have activation, you have pooling. Pooling reduce your usually they reduce you are pulling the side to reduce your dimension, right? And certainly at this time you should already increase your channels to prepare for this guy, right? So and to compensate for the reduce of dimension, increase your channel size, and so on. But basically, yeah, each one of that, eventually there's fully connected. Before fully connected, usually you could have another like layer, the pooling layer. Just say, let's say, eventually you end up with a 7 by 7 by 112, for example, right? 112 channel, 7 by 7 image, right? Assuming. And you could pull that to be 1 by 1 times 112, right? And instead of just leaving 7 by 7, you could do 7 by 7, 112, then you just multiply that together. It's becoming bigger, right? But sometimes you pull that again, just make sure you have a smaller, basically just the global average pooling. Sometimes do global average pooling in the end, just before the convolution. Yeah. Fully convolution layer, which I mean, this is basically this last layer, right? Just inputs. You have a linear activation. Linear kind of corresponding to the convolution, but there's no structure. There's no grid structure. Convolution has grid structure. It's a linear operation, but a special linear operation which using a much smaller number of parameters to perform regular grids. So here is a PyTorch. You can quickly go through that. Yeah, this one is one version about usually you define all this here, right? So in your init, you define, for example, first convolution layer, second convolution layer, first FC layer, second FC layer, right? So basically, and you do the convolution here. This one I think is MNIST, right? So 28, it's a one channel, starting with it's a gray image, it's one channel. And when you do a convolution, if you look at this convolution, it doesn't specify padding, right? And your in channel is 1. Out channel, you make it larger, right? So kernel size is 3. Without padding, you know that 28 by 28 is the input image, becomes 26 because there's padding is 0 here. So you reduce the size, right? And then you pass a nonlinear. Once you pass a nonlinear, you do yeah, this max pooling, yeah. Actually, I think it's first do the max pooling, then do the nonlinear. Basically, once you do this max pooling, you're starting from 13, right? So channel size is keep the same, which is out channel of is 4, right? 4 out channels, and the image dimension becomes 3 because it's a downsample by a factor of 2. Now you do another convolution. Another convolution you have after that, because again, we don't have a padding here. If we have no padding here, you're starting from 4 to 6. So you increase your channel again. This is in channel, is a C. 4 is the same as this guy. This is 6, right? So it becomes 11. After max pooling, there's one part you have to ignore after max pooling, right? So 11 divided by 2 is 5, becomes 5. So this one is max pooling. And so at this point, you have a 6 times 5 times 5, right? At this point. You could do another global pooling if you want, and then get a dimension of 6. Because 5 is 6 times 5 times 5 is small enough. So we just do that 6 times 5 times 5. Which flatten that dimension. So you get rid of all this grid structure, and you're just making it a large vector, right? And then you pass through the fully connect layer. Once you do this fully connect layer, you have this one, you have another one, these two fully connected. This using this size to 16, right? 16 to 10. 10 is the number of classes for the MNIST. It's a 10 digits MNIST. So basically, yeah. So that's essentially this is an interpretation of what you have done. And we will have an exercise. We will give a specific instruction how do you form the convolution and so on. But we will give the we'll have an exercise to build this kind of convolution, right? So in the homework. Okay, so that's now, I think this is pretty much we are covered the convolution. You just need to remember convolution, max pooling, ReLU we already seen, right? So then that's all. And the padding, you want to, whether you want to add that or not, right? So default is 0, it will reduce your image. For the 3x3 kernel, which is most typically reduce the image size by 2, right? And when you do the max pooling, reduce the image size by a factor of 2, right? So basically, yeah. So that's basically half your image size. Max pooling, I think because we usually say kernel size is 2 for max pooling. That's why. I mean, if you have 3, it's a factor of 3. But typically for the max pooling, you want to have 2. That's most typical. CN training, right? So that's quickly, I mean, this one is just repeating what we have talked about in the last lecture, stochastic gradient lecture. Basically, you have a regular loss, right? We have a weight decay. This one we mentioned, this is a weight decay. We just put it here, and we in the regular, basically, okay, in all the formulas, they don't explicitly using this weight decay, right? They just say specify in your optimizer, say weight decay, right? And then they will automatically have this effect. This is a CN. This is a loss function. It could be a softmax, whatever, right? So for the ImageNet, you have a 1,000 class. It's a softmax with 1,000 outputs, and this one is all the sum. And here is one way to do regularization for CN, which is pretty typical. You always can specify using weight decay. However, there are other ways to do regularization. We will talk about 2 things which are related to that. One is dropout. Another is the batch normalization. Right. So batch normalization is particularly they designed starting with this CN classification. So it will be good to know what those are. Okay, so let's talk about the dropout, and this is the paper. Basically, the idea is randomly disables a fraction of neurons during training. So this, why is that helpful? This actually quite a lot. This is not something you have to do, but in many, this always is a common layer now in the neural nets. You always have the option to do that. And in many cases, people try to do this kind of dropouts. And what it solves, we will soon and to talk about that. But basically in the scenes, right, activation is a feature map produced by convolution. Then you say, I will do a dropout to that. What it does is the following. So basically, according to these, just literally the words, right? So randomly disable fraction, what it does is the first at the feature map layer for all the feature maps, or all the output before your nonlinear layers, right? You are sampling basically before the nonlinear, right? So usually you sample each of the units or each channel outputs with a probability p, dropout probability, and basically you sample 0 or 1, right? P is the probability of keeping a neuron alive. You could make it a dead neuron. So what it does is doing this. This one the original paper using R times Z, the masking. This in the PyTorch implementation using R divided by P. So we will follow the PyTorch. The reason is once you do this, the inference is a little bit simpler. So otherwise you have to compensate by the inference. But here, if you do this, the inference will come to be simpler. So this is why I prefer that. But essentially, you modify the feature map as such. For example, here is your original, before the activation, you have original feature maps, right? These are for each pixel and for all the pixels. So you can think just your image, the total image size. For each of that, you have a mask. This is randomly drawn, right, by this R. 1 or 0 according to certain probability, just 0, 1. Now output for 1 you keep, for 0 effectively it's gone. So you can remove that from your training, or usually what basically people just do a 0 masking, so just times 0 because of the parallel of the GPUs. Yeah, you just times 0 is fine, and then you get this. So basically this is your output, right? So basically this is here. Again, you could do either scaling by 1 over p in the training, or you don't do that. Original paper doesn't do that. PyTorch does that. So we will follow this PyTorch, and this affects how you do the inference. So why it works according to the original paper? What it does is it's a simple technique, train neural net by randomly deactivating neurons. By the way, there's some mathematical derivation one can work with, so that to show there are some equivalence of this one with the regularization, L2 regularization in the certain cases. We will not go through that, but we just more repeating the original paper's motivation. Prevent specialization. Essentially, you are basically, in particular, the paper mentioned the collinearity. So two things simultaneous. Let's say if two neurons, they happen at some point they become very similar or identical, right? All the weights are identical, and below that and identical. Then what happens? You are not able to make it a change. So basically, these two neurons will keep identical always. If they are at some point it's identical, I mean both weights and outputs and so on. So this is called collinear. Basically, they are not doing different things. They hope the neuron doing different things. Basically they essentially they limit this co-adaptation. They are become too similar, and then they because of you randomize that, right? So eventually it give more noise. Once you have this more noise, they can break out anything which becomes collinear. So promote diversity. This one is the same, it's just a different. So it's a learn more diverse feature map. So that's always good. You don't want to stuck into something. There is also ensemble effect. It's like somehow if you average of all these, it's like ensemble of subnetworks within this model. So, but anyway, I think these two probably is more. Maybe I'll put these two on top, remove one of these, but essentially because these two are the more essential. It's just to explain why it works, and turns out that these are also related to the diversity regularization. Yeah. So we will talk a little bit about in the test phase what happens, right? Test space. So test space, what happens is the following. So you want to disable dropout. So why is that? You think a little bit about that. So what happens if you do not do that, right? You think about. So what if you don't do that? You have a random outputs, right? Unless you average of all the random, it's just to give you a random outputs, which is not desirable. Right? People don't do that. So therefore you disable. So this is actually what is disabling, telling disable that. If you think about when we recall, maybe we'll recall the test, we will see the loop again. Just recall when we do the testing feature, usually you do two things. No gradients, which basically you do not need to compute the gradients. There's a eval, right? Eval is actually what disabled basically tells dropout. If you have dropout layer, tells it that, oh, now it's a test time, you should be disabled, okay? So this is why you need the eval. And this is basically this guy, right? So in PyTorch, you have inverted the dropout in the training of, and for this one, your fully active data will be used with no scaling. So basically, dropout test data essentially doing nothing. So essentially, it's basically identity map. What if you don't do this, right? You can think a little bit about what if you don't do this in the training? What will happen, right? What do you want to do here, right? Yeah. So if you think about what you're doing, I mean, this one, why you want to do this? Basically, you want to take the expectation. Essentially, you are thinking about, let's say you have half the activation layers, right? If a training scaled by 2, this half behaves like the whole, right? If I don't do that, it's a half, right? If I half test, I should behave like half. Basically, this one, if you do not do this guy in the training, in the original paper, then you have to multiply by a p in the test. Test is not identical, multiply by p to compensate for that. But if you do this in the training, then this one doesn't have to be, okay? So this is how it works. Basically, which essentially means that, you either compensate by training or by testing. This one makes is half, for example, peak 0.5, you scale by 2, it's like each one behave like 2 neurons. So you don't need to do anything. Right. So basically, this one is, the answer is you have to times this by a p. Right. Basically, if you do this in the training, right, and the answer is time by p. Okay. So PyTorch example of this yeah, basically what do we do is the following, right? So you think about this convolution neural net. I have a dropout layer. Dropout of 0.5 means we have the formula. Basically, you skip half of your neurons in the training. right? You use all the neurons in the testing, but half neuron only in the training. Each time using different half in the training. Forward, you use first, you have a convolution, you have ReLU, you have this guy actually, this is a simple one. It's just for illustration. This guy is just, let's say, drop out after this. And then you do that, yeah. And yeah, basically, yes, yeah, basically you do the convolution, yeah. So, yeah. I think you can do both before and after. So for the dropouts, I think most for ReLU doesn't matter much, but for some other it somewhat matters a little bit. Yeah, but you can do that both. Yeah, it doesn't change too much. Yeah. Anyway, so this is what we are doing, and the model. Now when you do this eval, right? Just recall that eval when you drop out, it makes the identity. Right? Basically, when you go through this inference, dropout is disabled. It doesn't do anything. It just say identity map. So in the eval, okay. So any questions so far? Yeah.
On the feature map means.
Yeah, because your weight, for example, trained is 0.1, let's say, right? You apply a dropout factor, its effect become 2, it's like 2 neurons. You are thinking it's like already 2 neurons is acting together. Yeah. Right, so after nonlinear, you have, this is why it's after that, you have 2 things activation, right? Each one is, say, 0.1, it's your training, but I make it 2. This is not a trainable parameter, so it's a behavior like 2 in the training phase. It's like you are sampling the full thing, two things. But in the test, then you have to make it 1. Yeah. Basically, you have to make it consistent. Yeah. Yeah. Okay. Yeah. Yes.
Basically help the network escape local minima and like.
That's a good question. It's you can argue it's make it a little bit more diverse. Hopefully that will do that sometimes, but usually it's make it more stable. The training a little bit more stable. To be honest, the effect is minor. So, but people always make it a standard choice. You do see that even in transformers, sometimes people use, but sometimes people don't use. Yeah, yeah. But it can make it more stable. It's a very standard. Yeah, right. But scaling matters here. Yeah, you have to be either in the test you do scaling or train, because effectively if you use half effectively, you have to compensate somewhere, either in the training or in the test. Okay. Let's move on. So batch normalization. So this is, I think, the last topic. We will. Oh, it's not last topic. There is a real. There is ResNet, which we'll do quickly. This is another thing. Turns out, what's interesting is usually you don't do both batch norm and dropout, because they somehow not exactly compatible, but they both have the shared effect. And because people use batch norm more, right? So especially in CN, right? So in CN, you may not use. At least in the CN layer, in the final FCN layer, you could use the dropout, but the CN layer usually you don't. Yeah, because of the batch norm. Now batch norm. This is another form of regularization. It's actually very effective. It's kind of like in some sense a miraculously effective in the sense of something you cannot be trained before can be trained. So that's actually important. Yeah. The original thinking was it's reduce internal covariance shifts. We will talk about that. What does it mean? And stabilize accelerate training. This is actually true. Stabilize accelerate. In fact, with batch norm, typically you can use a larger learning rate. without breaking. Because when you use a larger learning rate, what happens is for certain problems, right, it can blow up the loss if you're too large. So you as we mentioned last lecture, you have to use as much as possible without blowing up. But also you have to decay in the end. But initially you want to use the larger one, right? And it turns out the batch norm will allow you to do larger learning rate without blowing up. Allow use of, yeah, so this is what? It's actually just one layer. The layer computes simple things. It's again, it's a per elements. So it's per elements, right? So each element, it's looking at one batch. So that's why I call it batch norm. You can do other things, but the batch is making it computationally easier. You look at the mean. You always normalize your x by subtract the mean divided by variance. So within each batch, you are trying to make sure this looks like a mean 0 and the variance, and then you compensate this shifting by another trainable parameters. Presumably, this should be a population mean, population variance, not the batch. But you know, for the typical implementation, you want using batch because that's much more convenient. Okay. Yeah, this is basically the way of how it's done. So why that is, and what is invariant covariance shift? And there's a simple picture what we can look at to explain. But basically, yeah, this is a formula, right? So and particularly with the ReLU, right? So these are learnable parameters. These are like a bias. This is like scaling parameters. This is both are vectors, right? This one you can think about the x vectors. So if you have image, right? Image you can say it's a c times h times w, right? Then you think that as a vector. Basically, element will be c times w times h number of elements. And then you have this dimension of vectors for each one, for each channel or each pixel. You have oh, actually for the CN it could be different. They could be only on channel. I have to look at that. Yeah, but essentially, yeah, this one is a this one is a vector. This one is that. This is a layer before the ReLU, right? Yeah. Yeah, for the first thing, I think it just work with channel. You could. But anyway, so the question is, what do you want to do with that? So here is the illustration of covariance shift. Basically, you know, if you look at your statistics, it's like this. Let's say you are drawing your batch statistics, something, they're all here. They all become 0. All become 0, then basically cannot be trained, right? So basically they are all the same. So for the ReLU function, what happens is 0, right? So what you want is you want this. One basically neural net is initialized because it's a random initialization. Usually we assure there the initial at the initial points, right? It's something like this happens. That's typically what happens at the initial when randomly initialized neural nets. But without the batch normalizer, after you are training, eventually they shift from here, which is desirable, to this one undesirable. And this why this is how it fixes. It's a kind of like in some way heuristic trick in some way, but nevertheless, this basically allows you shifts what's not trainable. This one you can say, oh, this one is similar to the effect of vanishing gradient, right? The gradient becomes 0, and then here you say, this one has a more sensible gradients. So basically, this is where we actually see the benefits about batch normalization. So basically, yeah, this makes training much faster because of this action. So this is just intuition. Now, what happens is the following. So, yeah, so basically, if you don't do that, what happens is you have a very slow convergence, right? Basically, if you don't do this, this one at least allows that to converge much faster. So something cannot be trained, it can be trained now. Yeah. And it's also more stable training if you do that correctly. Those are the empirical. Theoretically, there are some argument about it improve the smoothness of your function and what it does and so on. So we will not go over that. But empirically, this is what you do in the training. So batch norm training, it's a layer, right? So it's a BN to layer 2. You put a BN here. So basically within this layer, they're just doing input of that doing this, right? The question is where this guy comes from, right? I think I'm already mentioned that, but then what is the mean? What is the variance, right? There's a UB, which is compute the batch mean. Compute for each tensor, basically this one, yeah. I mean, usually, one thing I just want to say, usually when in the statistics, right, if you look at variance, it's divided by n-1, right? In practice, if you say, oh, I want to use batch normalization is wedge size of 1, then this one will break if you n-1. So you just use something like this. But still, it's not good for the batch normalization if batch size is 1 because this one becomes very small anyway. So usually when you do the batch normalization, you don't want to use a batch size of 1. You at least a reasonable size like 8 or like whatever 4, 8, whatever. Yeah, 32. Yeah, something like that. But generally, yeah, this is just batch statistics. This one is more from empirical. You say why theoretically this one has to be batch? Is that good? And they do see some observation about the usefulness of using batch statistics. Then actually, I can always say I use aggregate statistics rather than batch. Batch seems to be doing a little bit better. Somehow it introduced some randomness, like a dropout. Does it? This one also introduced randomness. Somehow this batch statistics turns out to work well. This is the first normalization methods used for come out for neural nets. This one is designed just for training CN. In fact, after this, there are many other works on normalization. Becomes important. People realize that around the nonlinearity, around that size, just like the covariance shift matters, right? The distribution matters. So there are other normalization, a transformer using a different normalization, which we'll come to, right? But then essentially, normalization is kind of important to make sure when you go through this nonlinearity, it's just not to try to make it behave bad, right? For example, covariance shift. It's just a clear example. If you go so always 0, it's bad. So you want to say, at least statistically, across different, I mean, you can say across a batch, or you say across other dimensions of your, there are different other dimensions over the image, for example, over the pixels and so on. And then you can say they are well behaved. Okay, so this is, I just want to comment on that. But this one is definitely the first one. This is very classical, so it's good to know what happens. And even now, I think there could be even new possibility to introduce new normalization. So if you are interested in playing with normalization to say to design better neural nets, that still may be possible. Yeah. The running mean and the computed moving average. Yeah. So this is for the training, right? This is for the this is a batch, but this one should be for the inference. Yeah, but yeah, yeah. So for the inference, you compute using run because this one is just for the training. As I said, you could use a running mean, average across many, but somehow people find that this one is certainly more noisy. But when you do the more noisy, just like drop out, somehow just happens to be good effects. But the running mean is still kept, right? It's not for training, but for the inference. So here is where it used for the inference. Again, in this case, you can see that training and inference are different. Training use a batch mean, right? Batch variance, and inference use a running mean, running variance, which is collected on your training data. This one turns out to be useful, and therefore, one thing about batch normalization, which is interesting, is the following. So you have a description of a training test. Therefore, when you do the eval, model eval, right, it will tells you whether you are in training mode or you're in evaluation mode, and these behave differently. So basically, you use different formula. The other thing about this one is maybe I'll just say a little bit more. More in the sense of because this one you can gather in the training data. Some people say, oh, maybe we should gather in the test data, right? Of course, that is a little bit of cheating, but then there's cases like domain adaptation, right? You say, oh, test data slightly shifting from training data, and this is the convenient parameters which you can run on the test data. Say, oh, it's a domain adaptation. You are shifting your data, and then you can do that. Yeah. So this is doable when you see this kind of simple formulas. Okay, so this is about it. So we talk about that. Okay. I think we are just giving you a quick look at batch normalization. And yeah, this one typically you do that before you do that before reloop. You could do that after reloop, but more typical before. Yeah, because the best this is more meaningful. Otherwise, the best for this some upon 0 when you have reloop, right? So basically, that's why it's usually is before. And there are some incompatibility of dropout. I don't want to mention that, but basically, I think that's about it. This one is for the forward operation and so on. Yeah, for CNN, dropout per channel, right? Compute the mean for the channel, right? Basically, yeah, across all statistics. So this is just a comment for the CNN. And during the inference, you do the running mean, so you have to eval. So we mentioned. We will quickly get, I think, a residual net. I think we a little bit short of time, but let's finish this. So this approach allows learn a residual function instead of overall function, making it easier to learn deep neural net. One thing is why is this? This is actually important structure, residual structure. Output is X plus this. A lot of doing that. Actually, there are some variations of that in other. Even in transformer, there's one variation of this residual structure, but also in the other structures. The original residual net is say they can learn much deeper neural nets this way. Why? You can think a little bit. You can treat it different ways, right? Batch norm somehow a little bit also you can think about handling the vanishing gradient. Residual is also handling this vanishing gradient. They all make it easier to train big, deeper neural nets. So for the residual, because there is a path of gradient from I, so you can never vanish in some way, unless this one is cancels this. That's very rare, right? But basically, you can always train. So that's a very intuitive, simple answer to that. Your gradient is always has this component's identity, so therefore it's not 0. And then you're adding something, you let it pass. Certainly, there are other things to say. Okay, you are making this one plus a smaller amount of this one is easier to learn, and each time you make a smaller amount adjustment, then you gradually adding more. One thing about the residual nets is that this one should be the same size, right? At least in this formulation. There are formulations you could do the downsample together, but because adding, so input output should be the same size when you do the addition. This one previous vanishing gradients, and that's why. And certainly the starting with the ImageNet classification and classical. We'll do a programming to do this. We will do a instruction step-by-step instruction to program one of the residual nets. But this one is a more classical one, address at 18, the specific structure about, they always using these blocks. This kind of blocks will have, each one is a residual block, so-called, and then you're repeating that. That makes it very, very deep. Right? This one, 18 is not that bit deep, but they have 52 and more than 100 or even 1,000 layers of these guys. Okay. Anyway, so I think yeah, we are pretty much done with this class, and these are the papers. Yeah, you want? Okay, thank you. Yeah, next time we'll do the sequence model. So.